Let's now look at exam questions that regard situations in which the particles are not in equilibrium. That is, in situations in which you have acceleration of the system. Okay, the first one is this one. This is from a spring 2012, question paper 41, question 6. It says particles P and Q of masses 0.6 and 0.4 kilograms respectively are attached to the ends of a light inextensible string. The string passes over a smooth pulley which is fixed at the top of a vertical cross-section of a triangular prism. The base of the prism is fixed on horizontal ground and each of the sloping sides is smooth, no friction. Each sloping side makes an angle of theta with the ground, where sine of theta equals 0.8. Initially, the particles are held at rest on the sloping sides with the string taut. The particles are released and move along lines of greatest slope. Find the tension in the string and the acceleration of the particles while both are moving. Okay, so you have no friction. All right, the only forces that you'll have is the weight of the particles and the tensions. All right, you will have what? What is the other piece of information that I saw here? They are held at rest at the beginning, so you know that the initial speed is 0. This is going to be important for question 2. All right? Again, I made a reproduction of this over here. In your exam, you don't have to do a reproduction. You can just work with the diagram that is in front of you. Let me put this bigger, otherwise you won't be able to see. Okay, too big. All right, so this is what you have. In particle P, you have the weight pointing down, and you have the tension along the string. You have a single string passing over a pulley, so the tension is the same throughout the string. So this tension over here is the same as that in magnitude as the tension over there. Okay. Because the mass of P is bigger than the mass of Q, and the angle is the same, the inclination is the same, you will know that this will go down and this one will go up. You know that from the start. It's not vital that you have this perception right now, but that's the way it is. So knowing that, I put this force, the horizontal component of this force, bigger than that one. Okay. I'm going to decompose the forces. Again, this is, you can think of this as a ramp. The x-axis will be along the slope of the ramp. The vertical, the y-axis, will be perpendicular to it. This will put the tension and the normal contact force over here with no need of decomposition. The one that decomposes is the weight. This is typical of questions involving ramps. Same thing over there. Okay? So focusing on point P, what is happening? You know that, horizontally speaking, this force, the horizontal component of the weight, must be bigger than the tension for this to accelerate downwards. On the vertical component, these two forces need to be the same because on the vertical axis, the particle is not moving, it's only moving on the horizontal axis. Okay? The opposite happens here. Again, in the vertical axis, the particle Q is not moving, it's just moving on the horizontal axis, again, along the slope. But in this case, this particle is going up, so this tension must be bigger than the horizontal component of the weight of Q. Okay? So you want to calculate the acceleration of the system. The best way for you to do this is to think of this as a single object. What do I mean with this? When you think of a system as a single object, you let go of the internal forces, which in this case is the tension. Imagine that you have like a cover. You cannot see this this wire, this string over here. You only see this going down and this going up with the same magnitude of acceleration, right? So what would you need to know? You need to know the weight of that one and the weight of that one in order to calculate the acceleration. As a whole, the mass of the object in this case is the string and the particles. The string has no mass, the pulley also has no mass, so the mass of the object as a whole is going to be the mass of P and Q put together. okay? And if you think of this as a whole, what do you have? You have one direction of motion, which is that way. Or you can think of this as the direction of motion, and the opposite as the direction that counters motion. What do I mean with this? I put all the forces that are taking this direction. See the motion of the mouse, okay? Up in this side, down in this side. You can think of this a little bit as kind of anti-clockwise, right? But think of this as one direction. And I'm putting this as positive. Everything that moves like this is positive. Everything that would move like that is negative. So this means what? This means that if you let go of the tensions, this component over here, the FG of, let me just see one thing. Yes, I made a small mistake. This is supposed to be P and this is supposed to be Q. Let me see if I can make this correction right now. Give me just 1 second and I'll do this correction right now. So this one over here is P. Okay, this is the particle that is pushing the other one. So I put this one as being positive. And this is Q. Okay, so Fg of P, x, the horizontal component, minus this one over here, equals the mass of the set, mq plus mp, times the acceleration. Don't forget, the acceleration of this, the magnitude of the acceleration of p, is the same as the magnitude of the acceleration of q, because they are connected by a light inextensible string. Okay? So all the other forces cancel out if you think of this as a single object. This minus that equals the mass of the object times the acceleration. It's just Newton's second law applied to this as a single object. Okay? So what is the weight of P and what is the horizontal component of this weight? Is m of P g sine of the angle. Okay? Is this part over here. Same thing goes for the Q. M of Q g sine of the same angle is the same angle. All right? Equals mp plus mqa. I factorized here g sine of the angle, and I simplified, and I finally substitute by the values, and I get the acceleration is 1.6 meters per second square. The question is also asking, besides the acceleration, the tension in the string, okay? Now that you want the tension in the string, you no longer may think of this as a single object. You have to focus on its parts. So pick one of them. I picked P, but you could work with Q as well. And what is happening with P? If you focus on P alone, what you have that this force minus that equals the mass of P times the acceleration that you just calculated. All right? You are just applying Newton's second law, but now to P alone. Make sense? And Newton's second law applies to the resultant force. You don't need to worry about what's happening vertically because these two cancel out. So the resultant force in what regards the y component is 0. The only one that is at play over here is the x component of these forces. Okay, so that's why I focus on these two alone. Fg of x minus the tension equals mp times acceleration. And you have everything except the tension, which is the thing that you are being asked. So I just expanded what this is, factorize a little bit, and then put all the numbers there, and I have the tension over here. Okay, next part of the question is, the speed of P when it reaches the ground is 2 meters per second. On reaching the ground, P comes to rest and remains at rest. Q continues to move up the slope but does not reach the pulley. Find the time taken from the instant that the particles are released until Q reaches its greatest height above the ground. So what's going on over here? What time are they talking about? The time you let this go, so there is time for this one to go down and hit the ground, which is the same that this takes to go up, from this moment onwards, you'll have a different situation. The physics of the question is going to change because you will no longer have the tension, right? This one hits the ground. This one, because of inertia, continues moving up. But then now the string is not taut, it's slack, so you lose the tension. So Q is going to slow down, is going to be slowed down by the weight, more exactly the horizontal component of the weight, until it stops at some point. So the total time that you need to calculate is the time for it to stop once P hits the ground, when the tension is gone, and the time taken for this one to hit the ground, right? Add these two, and is the total time that the question is talking about. I started with calculating the time taken after P hits the ground. Let me put this a little bit smaller now, okay? I know the speed at which this happens when it hits the ground is 2 meters per second. And after P hits the ground, Q continues to go up the slope under G sine of theta. This is the horizontal component of G. All right, G points down, but it's not the full extent of G, is not 10 meters per second square. That is being applied, so to speak, to Q. Is just the horizontal component of this weight. All right, it is, after all, on a slope. What is the horizontal component of this weight? Is G sine of theta. If this is G, this is the part that matters over here, which is G sine, is the opposite of this little triangle, sine of theta. Okay, so knowing that this is going to be the deceleration of Q, I can calculate the time. I know V, when it stops, the V is 0. I know U is the speed, the initial speed when P hits the ground, okay? When P hits the ground, its speed is 2 meters per second, is the same as the speed of Q, right? So I know this is 2. The acceleration, I just got an expression for it. The only thing I don't have is time. So substitute everything and I got the time. 0.25 seconds is the time it takes for Q to stop after P hits the ground. Now, this adds to the time taken when the particles were moving together, the time that took for P to hit the ground, which is given by the same expression. Now, V is 2, U is 0. Remember that the question told you that the system was at rest at the beginning. A, you just calculated on the previous question. So just substitute and calculate the initial time is 1.25. So 1.25 plus 0.25, the total time is 1.50. Okay? Next question. This is from a winter 2015 paper 41, and it's question 5. A small bead Q can move freely along a smooth horizontal straight wire AB of length 3 meters. Smooth again, no friction. 3 horizontal forces of magnitude F, 10 newtons and 20 newtons, act on the bead in the directions shown in the diagram. The magnitude of the resultant of the 3 forces is Rn in the direction shown in the diagram. Find the values of F and R, and then we'll look at question 2. So, actually, I took 30 seconds to think of this. The question doesn't talk about the bee having any mass. Actually, you don't even know if you are seeing this from above, from side. So there is no way for you to put any weight to Q. So you may assume in this case that the only forces acting on Q, on this small bead, are the forces that you have there. All right? And this resultant force is the outcome of adding these 3 forces over here. So there's no other force, hidden force, to be added in this situation. All right? Knowing this, you can reproduce the forces over here. Okay, so at green, I have the forces that were already in the diagram. Okay, the 10 Newton force, this F, the 20 Newton, and the R. Actually, I learned that the F is much smaller than the way it is represented in the question. Okay, that's why I put it here, much smaller. All right, this is the 20 Newton force. And this is, I always try to put the forces, the length of the arrows of the vectors proportional to their magnitude, so that visually or conceptually I can visualize the question in a better way, okay? And proportionally, this will be the size of the arrows, okay? So what do I know? I know that I need to decompose the forces. I picked this to be the x direction, the AB, and this to be the y direction, perpendicular to it, all right? The reason being because all the angles are expressed as referring to this side AB. So this must be one of the axes, the x-axis in this case. All right. So you know what? You know that if this is the resultant force, I can also break this down into a horizontal component and a vertical component. For this resultant force, the horizontal component of the resultant force is going to be R cosine of 15, and this is the horizontal component, and the vertical component, this one over here, is R sine of 15. Okay? And this is what? Don't forget, this is already the resultant force. It's not an extra force, a fourth force. This is the outcome of adding these three. Okay? So, for example, this R cosine of 15, the horizontal component of the resultant force, is the outcome of adding all the horizontal components of the three forces that you have. The 20 Newton force only has a horizontal component, but then this F over here is going to have its horizontal component, which is very tiny over there. It's F cosine of 70, all right? And is pointing in the same direction as to the right, so I assume that to be positive. But for the 10 Newton force, you have a horizontal component with magnitude 10 cosine of 10. Okay. Let me just see here one thing. Yes, it's not cosine of 10. It's cosine of 30. That should be 30 over there. Let me just, I don't know what I put 10. This is supposed to be 30. Let me just correct this very quickly. Otherwise, I will forget. So that is going to be x cosine of 30. And since it is pointing to the left, this is going to be negative. So right positive, left negative, and on y up positive, down negative. Okay, so what do I actually have on the horizontal side? I have 20 plus the f cosine of 70, both positive, minus the 10 cosine of 30, the one that is negative, must be equal to this r cosine of 15. Vertically, what do I have? I have this f now sine of 70. That's the vertical component of f. I have this now 10 sine of 30, and is pointing down, so must be negative, equals this r sine of 15, which also points down, I also put as negative. So the only thing that is positive is f sine of 70 minus 10 sine of 30 equals minus r sine of 15. Pay attention to the fact that if you would pick down to be positive, then this one will be the negative. It will be the same. You just have to be consistent from the beginning till the end. Okay, so I decided up was positive, down was negative. I'm keeping that, and the result should be the same. Okay, so now the physics is done, the mechanics is done. It's just calculations from now on. All right. So what do I want after all? I want the value of f and the value of r. Okay, so I don't know this, I don't know that. I know everything else. So I just substituted here. I leave it here for to use later. Okay, but I also have this equation, which I will leave with f sine of 70 as the subject. Okay, on the top one, I left f cosine of 70 as the subject. And now what can I do? When this happens, there is one trick you can do. you can divide one by the other, and you therefore eliminate, in this case, f. If I divide the bottom one by the top one, okay, in other words, if I divide the y component by the x component, I will have what? I will have f sine of 70 divided by f cosine of 70. So I cut out the f's, and what do I have? I have instead tan of 70, tangent of 70, which equals this divided by that. So I have a single equation in terms of r, which I will then go on to solve. Tan of 70 is this. I bring this denominator to that side. I expand. I put like terms in one side and the other term with just numbers on the other one, and I got r. Now that I got r, I go to this expression where I left it a little while ago, substitute it over there, and I get f. Okay? Second part of the question. Initially, the bath is at rest at A. It reaches B with a speed of 11.7 meters per second. Find the mass of the bead. There is one hidden information that is not represented here in the question, but is on the text, which is the length of AB is 3 meters. And now you use the laws of kinematics that you learn in the first or the second chapter to figure this out. This is a very simple one. You just need to know that the resultant force over here responsible for this motion to AB is just the horizontal component of this resultant force. All right? It's keeping the bead moving from A to B. All right? This is a horizontal motion, so you just need to focus on the horizontal component of the resultant force, which is r cosine of 15 equals ma. But you already know what r is, right? So what do you need to know? You need to know the acceleration in order to calculate the mass. To calculate the acceleration, you use this expression, this uvat, because you know the final speed, you need the initial speed, you know the distance, the only thing you don't know is the acceleration. So just substitute, you calculate the acceleration, then the mass is just going to be the value of r times cosine of 15 divided by the acceleration, which is 0.525 kilograms.